In the last video, we started talking about using rectangles to estimate the area under a curve between the curve and the x-axis. In this video, we're going to extend those ideas, talking about Riemann sums, but also considering maybe some ideas of review of sigma notation that we will use in the next section to create a formal definition for the integral. I'm actually going to talk about this in reverse order because I want to just extend from what we were just talking about. So in the last video, like I said, we were thinking about the area between the curve and the x-axis, but we were only looking at curves that were completely above the x-axis. In this first example, you're seeing that I've got a curve where part of it's below the x-axis and part of it's above. And I'm wanting to find this total area, everything in both of these regions together. I'm going between the interval of the point A and the point B, and I've got a closed interval. We could subdivide this into rectangles like we did in the last section, but if we do, we saw that we don't necessarily get the best estimate because anytime that I pick a particular part of um, a particular point for the height of a curve, I have different errors, whether it's an underestimate or an overestimate. But what if we were instead to choose the widths of the rectangles to not be the same? Like suppose I said, okay, I'm going to draw a rectangle here that's really skinny that fits up into this part. And then maybe I'll draw one that's a different width here, where I was able to kind of use what I know about this particular curve and have a lot of different sized rectangles to get the best estimate possible, where each of those widths are different. We're going to choose n minus 1 points to divide the interval between A and B into n subdivisions, and we'll label those points x sub 1, x sub 2, x sub n minus 1. We just need to have a labeling convention to say where they are. And we're going to call x naught x sub 0. That's going to be at A. And x sub n, that's going to be at B. And then all of the other points are going to be in the middle. So x sub 1 might be here, x sub 2 might be here, x sub 3, and so on. This is just emphasizing what I said again. At any particular point, we'll call it the kth interval somewhere. But notice that each of the widths of these intervals are not necessarily the same. We're using the Greek letter delta to indicate the change in between two values, two x values. So the change for x sub 1 is whatever this width is, that's going to be the base of our rectangle. And delta x sub 2 is also going to be the base of a different rectangle, not necessarily the same width. Just in general, thinking about what we were doing in the last section, we had our delta x's, the base of our rectangles was the same for every single one. And so in that case, we took the interval, which was b minus a, that would be the width of it, and we divided it into n equal subsections. Here's a picture of what this will look like. You can see that we've got a number of different rectangles drawn, and they all have different widths, trying to get the best estimate possible. We're using the midpoint process here, where we're picking a point in a particular interval. Let's say that we are looking at this one here. We're picking the point C sub k, which is in the kth subdivision. And when I plug that into the function here, that gives me the height of that particular rectangle. One thing to take into account is that when I'm above the x-axis, this value that I plug in is going to be positive. So when I calculate the area of that particular rectangle, I'm going to get a positive value. I'm taking a base multiplied by a positive height, I'll get a positive number. But if instead I was to look at this value, when I plug c sub 2 into the function, I will get a negative value. So the total area that I get for this rectangle is going to show up as negative below the x-axis. And similar to what we were saying in the last section, the more precise we make those rectangles, the smaller and the more subdivisions we create, the more accurate our estimate is going to be. The question for you to consider as we move forward into talking about integrals overall is what happens if we let delta x, the width of that rectangle, go to 0, if we let it get extremely small. What if we could get it so small that we ended up with just little tiny slivers that we were trying to calculate the entire area, just a very, very tall, a very small points at a time. The smaller we could make x sub 0, the more accurate we're going to get to the actual value of the area. All right, when we start talking about the idea of this integral that we're moving towards, taking these Riemann sums and making them really, really small in the width, we're going to be summing up a number of things. And so that's where this summation notation comes in. This is something that you probably covered in algebra or in pre-calculus, but I just want to go back and just kind of remind you of some of the notation. We are talking about the Greek letter sigma. It's a capital letter S, which indicates summation. We're taking a number of items and we're adding them together. The index here at the bottom tells us what our starting value is, and then up at the top, this tells us what our ending value is. And we use this as a counting mechanism. We're usually using integers, so I might be going between, let's say, 1 and 15. So 15 might be here at the top, and I'm entering k is 1, and then k is 2, k is 3, all the way up to 15. Here is the formula that we'll be plugging those numbers into to determine what we're adding together. Here are a couple of really simple examples. Looking at this first example, I'm starting at k equals 1, and the formula that I'm plugging it into is just take whatever input value and add them together. So in this case, I'm adding the numbers 1 through 5, and I get 15 as the final answer. Looking at the second example, I'm going between 1 and 3. This negative 1 to the k power is going to alternate between positive and negative values. So when I raise to the first power, I'm going to get a negative. When I raise to the second power, I'll get a positive, and so on. And then that second part, k, that's on the outside, we're just multiplying by 1, 2, and 3. Adding all of those together, I end up with negative 2 as a final answer. Looking down at the third and the fourth lines, we have things that are a little bit more complex. This is going just between 1 and 2. I'm plugging 1 in everywhere I see k for my first term. And then I plug 2 in everywhere I see k for my second term. Adding those together, I'm getting 7/6 for the overall summation. And then similarly here, for the fourth, I'm going between just the terms 4 and 5. I plug 4 in wherever I see k, and then I plug 5 in wherever I see k. So this is just kind of a reminder of how that summation notation works in a calculation form. Some of the rules that we'll be using are if I have two different summations and I add them together, if I have two terms, I can split them into two different summations. And same for subtraction in that second row. The constant rule says that if I have a constant c that's inside the summation, I can pull it out to the front and multiply the whole thing by that constant. And then number 4 is saying if I have a function that is a constant, like if I had, let's say, the summation as, let's say, k equals 1, up to 3 of the function 5, it's asking me to have 3 iterations of the number 5. So what I would have n, which is 3, multiplied by 5 to give me 15. This one right here is a real common summation that we come across. It's adding up just a string of numbers. Um, suppose I was adding up the numbers 1 through n. 1 plus 2 plus 3, yada, 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 all the way up to n minus 1 plus n. And what if I reverse the order? If I put n here and n minus 1 here, and then this would be 2, and this would be 1. So if I look at any one column like this, or even this one, when I add any column together, I get n plus 1. And I have a total of n columns of numbers added up together. And I have 2 sets of them, but I only want 1. I'm trying to add up just 1 set of them. So looking at this formula, each column total added up to n minus 1. There were n of them, and I have to divide by 2 because the way that I set this up to kind of show you how we get this formula, I had 2 of them, so I have to divide it by 2. So that's how we get that particular formula. And then down here, we've got the formulas for k squared and k cubed. You don't need to memorize these. We'll be talking about these as I said, when we start thinking about the definition of the definite integral. And we'll be looking at that next week. All right, thanks for watching, and I will see you in class.